Today you're going to draw some Lewis dot structures. I will let you read this part and I'll go right to the drawing of the structures. So the first thing you have to do is predict the location of all the atoms that are participating in the covalently bonded molecule. Hydrogen is always at the end. It only has a 1s subshell, and it can only take 2 electrons in that subshell, so it can only share 1 other electron. The least electronegative atom is the central atom, generally. Carbon is always the central atom. So find the total number of electrons available for bonding. That means you count the number of valence electrons. Determine the number of bonding pair by dividing the number of valence electrons by 2. Place one bonding pair, a single bond, between the central atoms and the terminal atoms, and dot the remaining electrons around their atoms.
All right, students, at this time, please release to the buses. Once again, students, all students need to evacuate the building and release to the buses.
Okay, let's draw these. So let's start with the diatomic element F2, and F2 has 7 valence electrons per fluorine, so that's a total of 14 electrons or 7 pair. So we draw the fluorines. We use one of our pairs to hook them together. That leaves 6 pairs remaining, and I start dotting the pairs around until an octet is formed. Fluorine has 2, 4, 6 electrons that are not shared and 2 that are. That is an octet. And that took up 3 of my electron pairs. So I have 3 more pairs for the other fluorine. And I see that it also has an octet as well. 2, 4, 6, 8 electrons. Okay, each of these hydrogens has 1 valence electron, and sulfur has 6 for a total of 8 electrons or 4 pair. Hydrogen has to be terminal. Another word for terminal is at the end. Another fancy term for that is a ligand. It means a hanger-oner. So I'm going to use 2 of my electron pair to connect the ligand to the central atom, which is sulfur. So that leaves me 2 pair to satisfy the octet. Hydrogen is satisfied with a duet, as we recall. It only has that 1s2 configuration, so that's all it can take. Therefore, I will satisfy the octet rule for sulfur by dotting my remaining 2 electron pair around the central atom. And I see now that sulfur has 2 electrons here, 2 lone pair electrons here, and 2 shared. So that's 2, 4, 6, 8. It has satisfied its octet rule. Ammonia has a nitrogen which has 5 valence electrons, 3 hydrogens for a total of 3 for 8 electron for 4 pair. All right, once again, hydrogen must be a ligand. It is terminal, so there we go. I'm going to use 3 of my pairs to connect the ligands to the central atom. That leaves 1 pair of electrons that are free to satisfy the octet rule for nitrogen, and they would go right here, and I can clearly see that the duet for the hydrogens have been satisfied, and there are 2, 4, 6, 8 for the nitrogen. Carbon tetrachloride has 4 valence electrons from the carbon, and it would have 4 times 7 from the chlorine, so that's 28, and 4 is 32 electrons or 16 pair. We recall our rules say that carbon is always the central atom, and the ligands in this case would be the chlorine molecules. chlorine atoms, I will use 4 of my electron pairs to connect them together, leaving 12 electrons remaining to satisfy the octet rule for all of the atoms involved. So starting here, I've used 3 on this chlorine, a total of 6 for this, 9 for this chlorine, and the last 3 around this ligand. I can see that all the chlorines have their octet satisfied with 1 shared pair and 3 lone pair, and the carbon in the central, as the central atom, shares 2, 4, 6, 8 electrons with the chlorines. F2O would have 14 valence electrons from the 2 fluorines, 6 from oxygen, which would be 20, or 10 pair. Oxygen will be the central atom. It is less electronegative than the very electronegative fluorine. I will use 2 of my pair to connect the oxygen to the ligands, and then I will dot the ligands. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons for a total of 10 pair. Here I have the perchlorate polyatomic ion. It is 1 chlorine and 4 oxygens. The chlorine has 7 valence electrons. The 4 oxygens each have 6 for 24. And they are telling us by this charge that 1 electron has been added for a negative charge. That's a total of 32 electrons, or 16 pair. Chlorine will be in as the central atom, and the oxygens will surround it. It's a nice symmetrical molecule. I will use 4 of my electron pair to hook them together. That leaves me 12 for my ligands. And that completes the octet rule for all of the atoms. I will surround this with a bracket and put a -1 charge to remind myself that an electron has been added to give this a -1 charge. All right, now we need to talk about those atoms that violate or are exceptions to the octet rule. I will let you read these. The important thing that you need to remember is any atom in period 3 or higher can exceed the octet rule, and when it does that, we say it expands the octet. Let's recall any quantum value of n greater than 3 or greater can expand the octet. Any thing in period 3 or higher has the subshell S, P, and D. And if you are these D valence electrons...
Kara Palermo, would you please call extension 4622? Kara Palermo, please call extension 4622.
That allow these atoms to expand their octet. So here we have PCl5, and PCl5 has 5 valence electrons from the phosphorus and a total of 35 from the 5 chlorines, for a total of 40 valence electrons, or 20 pair. The phosphorus will be in the central atom, and the chlorine molecules will kind of make a Ferris wheel in my little brain around the phosphorus. We will connect the central atom to its ligands by using 5 of our valence electrons. That leaves us with 35 electrons to satisfy the octet rule of the chlorines. And that should use up all of our remaining electrons? And it does. And we are done. And we will notice that the octet rule has been satisfied for all of the ligands, and the phosphorus has 2, 4, 6, 8, 10 electrons around it. It is capable of doing so because it is in period 3. Okay, I'm going to leave you to look at the book for this, and now I want to talk about a special condition, and that is when you expand the octet when you have too many electrons. And you put them around the central atom. You use multiple bonds when you have too few electrons around the central atom. So here's a couple of examples. Oxygen has 6 valence electrons. There are 2 of them. So that gives us 6 electron pairs to satisfy the octet rule. So we're going to decide one of these is a central atom. It doesn't matter to me which one you use. I always use the one on the left. I'm going to use one of my pair to hook them together, and I always start satisfying the octet with the ligands first. So I've used 3 of them. That leaves me 2 sets, or 2 pairs left over for the oxygen. I'm out of electrons, and I see that the ligand has a satisfied octet rule, but the central atom has 2, 4, 6, and that is not satisfied, so I will make 2 of the lone pair electrons share with the oxygen, and when I rewrite this, I then have a very symmetrical looking thing that looks like this. Now each one of the oxygens has its octet satisfied, and I've used my 6 pair. Alright, CO2 has 4 from the carbon and 12 from the oxygens for a total of 16 or 8 pair. Carbon's always a central atom, which means the oxygens are ligand. I'm going to use 2 pair to hook the molecule together. That leaves me 6 pair to satisfy the octet for all of these atoms, starting with my ligands first. I've used 3 to satisfy this oxygen. I will use 3 to satisfy the octet rule for this oxygen. I'm out of electrons, and I see that carbon only has 2 shared pairs for a total of 4. So I'm going to make the oxygen from each one of the ligands give up a pair of electrons to satisfy carbon's octet rule, and therefore the Lewis dot structure for carbon dioxide would look like this. Nitrogen is famous for having triple bonds. The diatomic molecule N2 has a total of 10 valence electrons, or 5 pair. When I make the left one the central atom, the right one the ligand, I use 1 to hook them together, 4 pair to satisfy the octet rule. 1, 2, and 3. That one's done, leaving me with 1 pair for this central atom, and that is not satisfying its octet. But if I make 2 of these lone pairs into shared pairs, I have a Lewis dot diagram that looks like this, and both atoms have 8 electrons associated with them, so satisfying the octet rule here. HCN would have 1 from the hydrogen, 4 from the carbon, and 5 from the nitrogen for a total of 10 electrons, or 5 pair. Carbon would be in the middle. You will attach the hydrogen and be done. Hydrogen now is a duet. The nitrogen would be here. I've used 2 pair, so I have 8 pair to satisfy the octet rule, or 8 electrons, 4 pair to satisfy the octet rule. 1, 2, 3, and I guess that would be 4. Or I can make, is that right? 1, 2, 3, 4, 5, 6. Oops, got carried away. There we go. This would be 6 pair altogether. 1, 2, 3, 4, 5 pair altogether. Wow. 10 divided by 2 is 5 today. I'm going to make these nitrogens share, and my complete Lewis dot diagram looks like that.